we introduced the idea, and we're going to break it up into two parts. The first part involves ideal situations in which there are no resistive forces. What that means is no friction, no air resistance, no internal heat that would take energy away from the objects in the system we're looking at. One way to say that is mechanical energy will be conserved in these systems. Now, in general, the law of conservation of energy says in a closed, isolated system of objects, closed means no objects leave or enter your system that you are not considering, and isolated means no outside forces act, no external forces act. All forces are accounted for in the system. In a closed, isolated system, the total amount of energy remains the same. It is a constant. Now, we're not going to delve into every single type of energy, every nook and cranny of your chemical energy of some cells in your body. I mean, we could get ridiculous. So we are going to simplify this and look at the total mechanical energy of systems, which means the total potential energy of a system. Now, that could include spring potential, that could include gravitational potential, and then plus all the kinetic energies. So if you have more than one object, you have to add all the kinetic energies of all the objects you have, plus all the potential energies. That is your total mechanical energy. So if we have friction in the system, that would not be included in the mechanical energy of an object. So an example of something we might see is a ball rolling down a track. So really we're only looking at the ball and the earth as a system, the earth bringing the ball down. And the total mechanical energy would be the potential energy of the ball, plus the kinetic energy of the ball at any moment. As an example, I want to look at a ball falling from rest. We're going to give it 100 joules of potential energy when it is at rest, which means kinetic energy is 0 at the top. Now this ball is 20 meters up in the air. So what happens when it falls? So the arrow is really going down. We're taking the ball and it's going to start to fall down. At this middle location, if we assume that the potential energy is 50 joules here, because it is at 10 meters high, what's the kinetic energy? Kinetic energy would also be 50 joules. Now, this is what we mean by mechanical energy being conserved. Since there's no energy loss to the air resistance in this idealized case, or any kind of frictional effects, this total energy up here at the top we can calculate as all the kinetic plus all the potential. Well, there is no kinetic. That's 0. And the potential is 100 joules. So the total energy is 100 joules at this location. Midway, when it falls to the halfway point, you also have 100 joules of total energy. When the ball hits the ground, we would say it has 0 joules of potential energy, as the height equals 0 at this point. Kinetic energy, therefore, when it strikes, is 100 joules. Now, when it pounds into the ground, a lot of heat is given off, and it would seem that the energy is totally destroyed, but we are really only considering the ball when it's falling in the air. We'll talk about heat energy in the next lesson. So as you can see, though, the total energy here is also 100 joules, and that's right as it strikes the ground. Kinetic energy would be 100 joules. Now, there's a little spot we missed, which is right here. And if we are given the potential energy is 20 joules, what's kinetic energy have to be? Again, we want to add up to 100 joules of total energy, so we know the kinetic is going to be 80 joules at this point. Kind of got off the page there. So kinetic energy here has to be 80 joules. 80 joules plus 20 joules, again, is a total of 100 joules. And that's what we mean by conservation of energy. And in this case, when there is no frictional effects, we're looking at the case where mechanical energy is conserved. The word conserved just means something is staying the same. Mechanical energy in this case is staying the same. If you look at the object as it falls, potential energy is lost. But that potential energy lost is equal to the kinetic energy gained by the ball. But the one thing we know is potential energy plus kinetic energy will equal 100 joules in the system defined. Take a look at another situation. This is kind of like the bowling ball demonstration I did in class. If we take the height to be 0 meters at this point, let's make this 1 meter and give this ball 5 kilograms of mass. Can we, as the ball swings down, determine the kinetic energy at the bottom? Well, we're going to do that using the same conservation law, and we'll assume no friction, no heat loss, which means mechanical energy is conserved, which means mechanical energy is a constant. So what we can say is the potential energy at A plus the kinetic energy at A must equal the potential energy at B plus the kinetic energy at B. That's the only way energy can be conserved. These are the initial conditions. These are the final conditions. Initial total energy equals the final total energy. Now, if we call B the 0 point, you should know by now that potential energy at B will be 0. And if we assume we're dropping this ball from rest, or letting it go from rest, then equally you should know that kinetic energy at A is 0. So really what we're saying here is all the potential energy stored at A, which is mgh at A, is equal to all the kinetic energy stored at B. Not stored, but the kinetic energy of the ball at B, the moving energy. 1/2 mv squared at B. So plugging in the numbers here, we say we have a mass of 5 kilograms. G, we're using 10 meters per second squared instead of 9.8. And H, 1 meter. That's going to equal this kinetic energy at B. Now we can break this apart and solve for the velocity if we want to. Let's just get the kinetic energy here to begin with. 50, this would be 50 joules. Or 50 kilogram meters squared per second squared, that's 50 joules. Energy is not a vector quantity, there's no direction associated with that. So that must be the kinetic energy at the bottom. So this illustrates how you would use the law of conservation of energy, and this is in the conditions of no heat loss, no friction, to solve for systems in which the objects are changing in some way. Here we were able to solve for the kinetic energy at the bottom by assuming it's equal to the potential energy at the top. Energy is conserved, potential gives way to kinetic. Now, how would we solve for the velocity, or the speed, of the ball at B? Well, knowing the kinetic energy is 50 joules, or 50 kilogram meters squared per second squared, we can say that the kinetic energy of the ball at B, this is at B, will equal 1/2 times m, the speed of the ball at B, squared. So we just determined that we have 50 joules, or 50 kilogram meters squared per second squared. I will not always be putting the more cumbersome way of writing the unit. I'm doing that to show how the units work out in this case. So we have 5 kilograms, and we can solve for the speed at the bottom. So this is 2.5 and 2.5 kilograms. VB squared equals 50, same unit. So it would be 50 divided by 2.5 equals 50. Now 50 divided by 2.5 would be the same as 500 over 25. I think that would be 20. Kilogram's going to drop out, and you're going to have meters squared per second squared. V sub b equals the square root of 20, which is about 4.47. And then you take the square root of the units as well. You get 4.47 meters per second. So we looked at a situation where all we knew was the height and mass of the bowling ball at A versus B. We used the conservation of energy to solve for the kinetic energy at B from the potential energy at A. And knowing the kinetic energy at the bottom allowed us to solve for the speed of the ball. So we completely defined the system using conservation of energy. One of the advantages of this system is it's much easier than using forces and Newton's laws, which involve the net force and the acceleration, which is very complex in a situation where you have a pendulum. The acceleration is not constant, it's changing. So it is not easy to solve. Conservation of energy gives us a leg up. On the next video, I'm going to demonstrate, this is kind of a not so clear picture. We have a wall, we have a spring attached, and attached to the spring is this ball. And then we're going to move this ball, which requires a force, which means we do work. And that's going to compress the spring to this point. It's going to give the spring potential energy, and then in letting go and releasing the ball will kind of like a dart gun or a BB gun, it's going to project back to the left. We're going to see how conservation of energy can be used to solve that in the next video. So hopefully this went well. First time. We'll see. Britain out.